I'm going to give you kind of a breakdown of what chapters we're going to cover and what sections we're going to cover. So before I do that, I want to talk about 1.1. It's not a long section, even though I'm probably going to make it longer than it has to be. But it kind of gives you a feel for what we're doing in this course and what we want to get accomplished. There's basically two problems that calculus solves that we weren't able to solve without calculus. The two problems are the tangent line problem and the area problem. I'm going to show you what these two problems are so you know what we're trying to do in this class. Let's start with the tangent line problem. So let me give you an example. So let f of x equal x squared. So I just picked some random function, x squared. That's good enough. I'll give you a couple of different calculations to make here. Find the slope of the secant line to the graph of f, to f, between x equals 1 and x equals 2. What does this even mean? How can we approach it? What's f of x equals x squared look like? Let's start with that. A u, a parabola, yeah, something like that. So in my head, I have a picture going on because I like pictures. Makes me feel like I know something. Here's x squared. I'm asking you to find the slope of the secant line to this function between 1 and 2. Maybe you know what a secant line is, maybe you don't. It doesn't really matter. There's only so much you can do between x equals 1 and 2 on this graph. Right, if you go to x equals 1 on your graph, you're at this point, 1, 1. How do I get that? Squared is 1, right? Plug it into the function. F of 1, 1 squared. If I go to 2, 2's out here, what do I be at? 4, right? 2 squared. So because the question is asking for slope, pretty much the only thing I can be asking you to do is find the slope of the line that goes right through these 2 points like this. A secant line, sort of the definition of a secant line, it's a line that goes through a graph or a line that touches a graph twice. 2 different points. What's the slope of this? Very easy enough, right? y2 minus y1 over x2 minus x1. 4 minus 1 over 4 minus 1 over 2 minus 1. Okay. So now I have similar questions. I want you to repeat, do the same exact thing. But go between 1 and 2.5. And then let's do between, oh, not 2.5, 1.5. And then we'll do between 1 and 1.1. So what I'm saying is if I change my point, if I change my second x value, but I've kept my first x value the same, but but I want to change my second x value. Instead of 2, I want to go to 1.5. What will this point be? 1.5 comma 2.25. You just square 1.5. So what's your slope here? Or how would you calculate it? 2.25 minus 1 over 1.5 minus 1, which is 1.25 over 0.5. What's that decimal? Two point five. So what happened to our slope? It got smaller. Okay, which makes sense, right? Because if you look at this new tangent line, it's not quite as steep. 1.1, I'm sorry, the secant line. 1.1, even worse. 1.1, I'm sorry, even smaller. 1.1 is really close to 1. So what point is that going to give you on the graph? 1.1 comma 1.21, right? Because do 1.1 squared. So what's my slope here? Well, you just do the slope formula. 1.21 minus 1 over 1.1 minus 1. So 0.21 over 0.1, 2.1. So even smaller, which makes sense. Right? If you graph this line here, you'll get a less steep slope. So part C is the tangent line problem. Right? The whole reason the first three chapters in this book exist is to solve the problem, what's the slope of a line that goes through 1, 1 and only hits this graph once? And this is called the tangent line to the graph. At x equals 1. So the tangent line is going to be the line that doesn't go through two separate points, but only goes through that one point on the graph. Just kisses it right there. So it's going to have a slightly less steep slope because the blue line is actually hitting at 2 points. So you have to keep coming down a little bit, little bit, little bit. Can you guess what the slope of this line is going to be? 2. These are somehow, I mean, you could do more calculations, right? You could do 1.001, 1.0001, and try to get an estimate, right? Just by lowering this guy closer and closer to 1, you get a decent estimate. But at the end of the day, right now, all we can do is guess. By the end of chapter 2, actually by section 2.1, you'll be able to calculate using calculus exactly what that slope is. But right now, we don't have the technology. You need something called a limit. And we don't have the technology to figure out exactly what this is. But that's what we want to get to. Okay? Given any graph, any function in the world, I want to be able to find the slope of the tangent line at any point. And that's going to tell us a lot about the graph, right? Because one thing, what do you notice, for example, right? Let me draw another graph because this is getting kind of messy. Let me go over here. Here's x squared. Something like that. If I draw a tangent line over here, so remember, a tangent line only hits your graph at one point. If I draw a tangent line over here at, say, x equals 3, versus a tangent line over here, so I go to negative 3, draw my tangent line. Like that, only hits my graph once. What's the difference between those two lines? The sign. One's positive, one's negative. Right? This line's going up, this line's going down. So these are both tangent lines. And that corresponds to a difference in the graph. Right? On the right side of 0, when x is greater than 0, your graph is increasing, it's going up. It's got a positive slope. No matter where you draw this tangent line, it's going to have a positive slope, therefore your function is increasing. Over here, your function is decreasing. So slopes of tangent lines help us determine when a function is increasing or decreasing. They're also going to help us get at these relative maximums and relative minimums. If you can find a formula for the slope of the tangent line, then you can find the exact place where the tangent line is horizontal. And if you can find where a tangent line is horizontal, then you know where you have a relative maximum, relative minimum. So this is what chapters 1 through 3 actually focus on. Okay, the tangent line problem, being able to find the slope of the tangent line to any function at any point. So good? Questions about what I did? So I only assigned 2 problems in this section, just because there's not really a lot of math to it. It's more introduction of what we're going to be doing. But one of them is to find the slope of a secant line and then guess at the slope of a tangent line.
We have 5 and 7.
Yeah. If you have trouble with those, ask me next time.
Would it be 6? That one.
Oh, is it 6?
For the other one.
Oh, I don't know. What would be 6?
The tangent line. The slope would be 6.
Where would the slope be 6?
X equals 3.
Yeah. How'd you get that?
Because on that one you're at 1. So if it was like, if the slope is 2, it would be like 2, 1. Would be the slope of like the line. So it'd be like, the slope of the line would be like m equals, or it would be like the graph of the equation of the line would be like y equals 2 parentheses 1.
Right, yeah, so the slope of this has a nice formula that if you double this x value, you always get the slope of this. So if I went out to x equals 6 and I doubled that, my slope would be 12. So that's kind of the structure of this graph. As the graph changes, that structure changes. Okay, if I give you a cubic graph, it's not quite so simple. You know what I mean? But yes, that is the structure of this graph, absolutely. But we'll be doing a lot of tangent line problems, don't worry. Let me talk about the area problem. So find the area. So I'll do a couple parts. A, find the area under the graph of the line y equals 2. From, I need to give more information than that. That's interesting. From x equals 0 to x equals 1. So this is something you can do. Right? Just like before where I asked you for the slope of the secant line, that was something you can do. So we're going to start with something you can actually calculate. So I give you y equals 2, which you all know, hopefully, is a horizontal line. And what I'm asking for is the area underneath the graph of that line between x equals 0 and x equals 1. Here's x equals 0. Here's x equals 1. So I want to know this area.
2 square units.
2 square units. It's a rectangle, right? You can calculate the area of a rectangle. I hope. Or else we have our work cut out for us. So, this, let's say, length, width. Right? So A is L times W. But I know my length is 2, I know my width is 1. So because it's area, you know it's squared units. If the area is 2. Easy enough. Now let me give you something you can do, but leads to something you cannot do. So estimate the area under the graph of y equals x squared between 0 and 2, x equals 0. So now I have a more complicated graph.
So we treat it like a triangle.
You could, so this guy is not a straight line, right? Okay. So one suggestion is to treat it like a straight line and make a triangle. That's an okay suggestion. Okay, it's going to do a little bit better than what I'm going to do. It's actually better than what I'm going to do. But what I'm going to do leads us to what we're going to be able to do later, so I'm going to do a little less work than that. I'm going to say, you know what, I'm too dumb to know the area of a triangle. All I know is the area of a rectangle. So I'm going to make a terrible estimate at the area under this guy. Right? This is between 0 and 2. Here's 0. Here's x equals 0. Here's x equals 2. Here's the area I care about. Right here. I'm going to make an incredibly crappy estimate by using rectangles. I'm going to first draw a rectangle at x equals 1. I'm going to draw this rectangle by going up to the graph at x equals 1. Let me shade that in there. And then I'm going to, since I missed this portion of my area, I'm going to draw another rectangle at x equals 2. So go up to where I intersect my graph, but only go down to 1. This is an extreme overestimate. But it's an estimate. That's what I'm going to start off with. If I want to estimate it this way, what would my estimate be? How do you get it?
Down 1 plus down 1 all over 2.
So I'm not going to cut it in half because that would be using triangles. No, I can calculate it. I can calculate the area of each of these. That's what I want to do.
Add them together.
Yeah. So what's the area of this first rectangle? This. Why? Because the height is 1, right? If you go up to your graph and you plug in 1, you get out 1. So this is 1. What's the height of this second guy? 4, right? This guy goes up to 4. The y value is 4. Because 2 squared, 2 squared is 4. And 4 is right there, 1 is right here. So then I can calculate the area of the first rectangle, length times width, 1 times 1. And then add to it the area of the second rectangle, length times width, 4 times 1. This distance here is 1. This distance here is also 1. This distance here is 4. This guy here is 4. So I get 5 for my estimate of area. Incredibly terrible. In fact, if you cut it in half and took 2.5, that would be a much better estimate. But we're not going to. This is what we're going to say. We work for the government. We don't have to be accurate. But keeping with this idea that the only thing I know is how to calculate the area of a rectangle. That's all I ever learned. How could I make this estimate better? Do more rectangles. Right? If you use more rectangles, your estimate should get better. And so I'm going to estimate the same area, but I'm going to use more rectangles this time. So here's 2. Here's where my region stops. So I'm going to calculate the area of this region, figure out a way to estimate it. But instead of using a rectangle that stops at 1, I'm going to break this into 4 different segments and use 4 different rectangles. So I'll stop at 1 half, then 1, then 3 halves. And then eventually I'll make it to 2. So now I go up to my graph at 1 half, get that area, go up to my graph at 1, get this area, go up to my graph at 3 halves, get this area, and then go up to my graph at 2, and get this area. So it's a little bit better estimate because I've cut off how much I'm overestimating by, right? There's not quite as much on top of the graph that there was here. So my estimate for area would be the sum of my 4 rectangles, right? I need to do area 1 plus area 2 plus area 3 plus area 4. And do each one of these individually. 4 rectangles. Now this, let's see, we actually have to calculate these heights here. What's the height or the length of the first rectangle?
1/4.
If we do 1 half squared, right, to get the height of this rectangle, to get how tall this is, because that's where it intersects the graph when you do 1 half squared. 1/4. Right, so when you do length times width for the first guy, you're going to do length is width, I guess, is 1 half, but this distance here, I'm sorry, 1/4. But this distance here is 1 half. See that? So this will be 1 half times 1/4. You square 1 half to get this guy, and then you just take 1 half as the width for this guy. What about for the second area? 1 half, again, because the rectangle is 1 half long, times 1, because if you square 1 to get your y value, you get 1 again. 3 halves squared will be the height here, and 1 half will be the width. And what's the last one? This guy's up at 4 if you square 2. Let me calculate out what this is. So 1/8 plus 1 half plus 9/4, 9/8 plus 2, 10/8 plus 2 plus 1 half. 38. Did you 40?
Sorry,
38? Yeah, so we can reduce that 15/4. Should be 3.75, that's it. Now, this is an incredibly tedious process. And when you do it in chapter 4, you're going to find it incredibly tedious then too. Fortunately, this is still an overestimate, and we still want to get the exact area one day. Okay, so fortunately, we're going to have sort of a shortcut. After we do all the grunt work of estimating area like this, we can take a shortcut and get the exact area you calculate. The way that what the shortcut comes from is actually extending the number of rectangles you use. Right? Instead of using 4, if you use 8 rectangles, even better estimate. If you use 16 rectangles, even better. Use 1,000 rectangles, you're pretty much right on. So the more rectangles you use, the smaller this width gets. What ends up happening is you get something more like here's 1 rectangle, 2 rectangles, 3 rectangles, 4 rectangles. Right? They're so small that they don't have any overestimate, or barely any overestimate. The actual answer to this problem, by the way, comes from taking the integral, which is what we learned in chapter 4. This is what we're going to learn how to do. So at one point in your career, if you stick with this class, you'll know what all of this means. Of course, if you drop, you won't. Where did I get the 1/4? Where did I get the very first 1/4? Squared 1/2. Because if you have to go up to your function here, and since your function is x squared, you have to square this. 1/2 squared is 1/4. So that's where this is coming. So this guy is 1/2 squared. This guy is 1 squared. This guy is 3/2 squared, but I didn't calculate it here. Which would be 9/4 to follow the same format. And this guy's 2 squared. Okay, so you're squaring each of these numbers here.
Question. You didn't explain that last line.
Oh,
You just said
it's magic.
going to be a measurement. Magic. Okay.
It's magic. The area should be 8/3.
Did I miss that much? Stepped up.
This is what we do in chapter 4. So if you take your width of your rectangle and be infinitely small, if you put an infinite number of rectangles, you can get the actual area. Until then, you're just doing crappy estimates. Right? Until these widths get infinitely small, you're just doing estimates.
So is that like the reverse of what we did the first
Yes,
time?
that is the reverse of what we did in the first one.
How about the homework problem, though it's not rectangle? Maybe a different one.
It asks you to estimate the area under a graph, and you can do it using rectangles. If the homework problem is ever not what I say it is, then just ask me the next time you see me. I will give you an aw shucks grin and help you with it. All right, guys. So this is kind of the 2 problems we want to solve. Like I said, 1 through 3 is focusing on the tangent line problem. More specifically, and we'll start 1.2 right now, but a little bit more specifically what's going on here. Chapter 1 is about what's called limits. Okay? So this idea of where you can take the number of rectangles to an infinite number, or the idea in the tangent line problem where you put one x infinitely close to another x, that's a limit. So we actually don't, even after chapter 1, we won't have enough technology to talk about tangent lines, but this will help us get there. But chapter 2 is about the derivative, which is another name for the slope of the tangent line. This is what we do. Chapter 3 is applications of derivatives, like graphing and maximizing. Chapter 4 is integration, which is this. Chapter 5 is derivatives and integrals of transcendental functions. So like exponential functions and log functions.